Okay, so let's start. So we're going to talk about section 14.2, which is the fundamental theorem of Galois theory. So first of all, I'm going to review some theorems and corollaries before the fundamental theorem of Galois theory. And then I'll start speaking about the fundamental theorem of Galois theory. And then I'll probably get to some examples. So first is theorem 9. Let G be this subgroup of automorphisms of a field K. And say the order of G is n. So there are n different automorphisms of K. And let F be the fixed field of G. Then the degree of the extension K over F is equal to n, which is the order of the group. So the way the book proves this is by using some linear independence of characters. I think Eric used a different proof, but yeah. This is just saying that if you have a field and you have a subgroup of automorphisms, then the degree of the field over the fixed field is the order of the group. Now this theorem has a bunch of corollaries. First, corollary 10. Let K over F be any finite extension. Then the order of the automorphism group of K over F is less than or equal to the degree of the extension K over F, with the quality if and only if F is the fixed field of the automorphisms K over F. i.e., K over F is Galois if and only if F is the fixed field of the automorphisms of K over F. So previously we saw that if having a splitting field, the order of the extension K over F is going to be equal to the degree of the extension. In the case, it's a splitting field of a separable polynomial. And now we know that for any finite extension, the order of the automorphism group is less than the degree of the extension. And again, this is a corollary of theorem 9 because theorem 9 says the degree of the extension is equal to the group of automorphisms when the base field is a fixed field. Okay. So another corollary, let G be a finite subgroup of automorphisms of a field K, and let F be the fixed field. Then every automorphism of K fixing F is contained in G, i.e. the automorphism group of K over F is equal to G. So K over F is Galois with Galois group G. So what this is saying is you have G, a subgroup of automorphisms of the field K, and F is the fixed field. Then K over F is a Galois with with Galois group G. All right. Corollary 12, if G1 does not equal to G2 are distinct subgroups of the automorphisms of a field K, then their fixed fields are also distinct. Okay, so corollary 10, 11, and 12 are all corollaries of theorem 9. And yeah. All right, now theorem 13 is a different, is about splitting fields. So the extension K over F is Galois if and only if K is the splitting field of some separable polynomial over F. Furthermore, if this is the case, then every irreducible polynomial with coefficients in F, which has a root in K, is separable and has all its roots in K. So in particular, K over F is a separable extension. Right. So what this is doing is giving an alternate characterization of Galois extensions. So K over F is Galois if and only if K is the splitting field of some separable polynomial over F. And if this is the case, then every irreducible polynomial with a root in K is separable and has all its roots in K. So it's a separable extension. So now we have 4 different characterizations of Galois extensions. 1, splitting field of a separable polynomial over F. So this is given by Theorem 13. 2, fields where F is precisely the set of elements fixed by K over F. This is one of the corollaries above from Theorem 9. 3, fields with the degree of the extension being the order of the automorphism group. This is the original definition. And 4, finite, normal, and separable extensions. This is also given by Theorem 13 in this second statement. So now let's talk about the fundamental theorem of Galois theory. So let K over F be a Galois extension and set G to be the Galois group of K over F. Then there is a bijection, and the bijection goes from subfields E of K containing F, so these subfields lying between K and F, and subgroups H of G. So G is the Galois group of K over F, and H is a subgroup of G. This bijection is given by correspondence. E, the subfield, gets mapped to the elements of G fixing E, and H, the subgroup, gets mapped to the fixed field of H. And these correspondences are inverses to each other. Now, there's a lot more to the fundamental theorem. So under this correspondence, 1, it's inclusion reversing. If E1 and E2 correspond to H1 and H2 respectively, so if this subfield and this subfield correspond to this subgroup and this subgroup respectively, then E1 is a subfield of E2 if and only if H2 is a subgroup of H1. 2, K, the degree of K over H is H, and the degree of E over F is the index of H and G, the index of H and G. So this is always the case, right? The degree of K over E is H, right? Let's go back to this correspondence. How do you go from H to E? E is the fixed field of H. So if you have E being the fixed field of H, then the degree of this extension is H. And the degree of E over F, this extension, is G over H, the index of H and G. 3, K over E is always Galois with Galois group Galois of K over E, which is H. Right? So if you have a Galois extension K over F, then any subfield you have a Galois extension K over E for any subfield. 4, E is Galois over F if and only if. So what is this statement about? We have K contains F contains E, K contains E contains F. F is the ground field, and now we're talking about this extension, E over F. We always know K over E is Galois. Now we're thinking about this case where E over F. So we're saying E over F is Galois over F if and only if H is a normal subgroup in G. So this statement told us that E over F has degree the index of G over H. And now if H is normal in G, then E over F is Galois. And in this case, the Galois group is isomorphic to the quotient group. So not only do the orders match, but you have this isomorphism between the Galois group E over F and the quotient group G over H. So I think 4 is 1, 2, and 3 are pretty straightforward to prove. We'll get to that. The correspondence is a bijection. We'll get to that as well. And 4 is, I think, a little bit more involved to prove than 1, 2, and 3. but we'll get to that. And 5 as well. So, all right. So 5 says if E1 and E2 correspond to H1 and H2 respectively, then the intersection E1 intersect E2 corresponds to the group H1 adjoin H2. So this is the subgroup generated by H1 and H2. So if you take the intersections of the subfields, then they correspond to the like join of two subgroups. Okay, and the composite field E1, E2 corresponds to the intersection H1 intersect H2. Hence, the lattice of subfields of K and the lattice of subgroups of G are dual, in the sense that the lattice diagram for one is the lattice diagram for the other turned upside down. Okay, so those are the 5 statements that make up the fundamental theorem of Galois theory. So to repeat, you have this bijection between subfields and subgroups given by the correspondences of taking the element, looking at the automorphisms that fix E and looking at the fixed fields of a subgroup. And then this is inclusion reversing. The order of an extension is the order of the subgroup, and the order of the other extension is the index. These extensions are always Galois, with Galois group being the field, the subgroup. If H is normal, then this extension has is Galois and has Galois group being the factor group. And finally, the two lattices are dual. Okay, now to the proof. So I didn't get to writing out the whole proof, but I guess I'll try to figure it out as we go on. So the first thing we're going to try to prove is that the correspondences are inverse to each other. All right. So let's see. So we have these two correspondences, one going from the subfields of E containing F, and the other one going to the domain being the subfields of E containing F, and the subfields of K containing F, and the subgroups of A is subgroups of G. Right. All right. So first step is we're going to prove that the forwards correspondence E getting mapped to the elements of G fixing E, that this is injective. Right. So what is this action? It's taking E and then getting the elements of G fixing E. Wait, actually the other way around. I want to prove that this correspondence is injective. So we're starting with H and then going to the fixed field of H. So I want to show that this is injective. All right, so let's start. Given any subgroup H of G, right, we obtain a unique fixed field E. Right. So E is going to be equal to the fixed field of H. Okay. Apparently this was corollary 12. So this shows that the correspondence is injective from right to left. All right, now we have to show that the correspondence from right to left is surjective. So we proved that the correspondence from right to left is injective. Now we're trying to prove that the correspondence from right to left is surjective. Okay, so we're going to use an alternative definition of Galois group, which is a Galois extension, which is saying that K is a splitting field of a separable polynomial f of x. Right. So, K is splitting field of separable polynomial f of x with coefficients in f. So that's another way to say that you have a Galois extension. So what do we want to do? We can view f of x as an element of E of x because the field F is contained in the field E. So K is also the splitting field of a separable polynomial with coefficients in E. Yeah. So K over E is Galois. Right. Now we're going to use corollary 10 to get that E is a fixed field of the automorphism group. No, E is a fixed field of the automorphism group. So sorry. So every subfield of K containing F arises as the fixed field of some subgroup of G. So what we showed is that every subfield E arises as a fixed field of some subgroup of G. So we have a surjection and thus a bijection. Are any questions about that? All right. So yeah. And then furthermore, these correspondences are inverse to each other since the automorphisms fixing E are precisely automorphisms K over E by corollary 10. Okay. So now let's prove one. One says that's inclusion reversing, and we already did this before, and it was proposition 4. Now, 2. What was 2 about? 2 was about the order of the extension E over F, the ground field. So you have E is a subfield of K, and we want to prove that the degree of E over F is the index of H in G. Okay. So if E is K over is the fixed field of H, if E is the fixed field of H, then theorem 9 gives that the degree of K over E is the degree of H. It is the order of H. Theorem 9 was the very first theorem that we did. We talked about today. If F is a fixed field of K of this group G, then the degree of K over F is the order of G. So by theorem 9, since E is a fixed field of H, the degree of K over E is the degree of H. And the degree of K over F is the degree of G. This is by definition of Galois. Now, what is the degree of E over F? Well, since you have um, if you take the degree of E over F times the degree of K over F, you're going to get the degree of K over E. Wait, no. I mean, if you take the degree of K over E and multiply by the degree of E over F, you're going to get the degree of K over F because of the multiplicativity in towers. So the degree of H times whatever this is the degree of G. So whatever this is G divided, the order of G divided by the order of H. Okay. Um, yeah. All right. Now, proof of 3. What is 3 about? 3 is that E is a subfield of K, and then the Galois group of K over E is going to be H. Okay. And this is, again, corollary 11. Uh, Corollary 11, which was about yeah. So if you have the fixed field of a group, then K over F is Galois with Galois group G. All right. Now let's do proof of 4. So what was 4? 4 is the thing about the the fact that E is a Galois over F if and only if H is a normal subgroup in G. And in that case, the Galois group E over F is the isomorphic to the quotient group G over H. All right. Okay, so the proof of this is like a page long. I'll try to decipher it as we go along. All right. Suppose E is the fixed field of H. Right. Every sigma in G which is the Galois group of K over F, when restricted to E, is an embedding of E with the subfield. Uh, so it takes E to sigma of E, which is a subfield of K. Okay. Conversely, let tau from E to tau of E be any embedding of E into a fixed algebraic closure F bar. Then, all right, so now, all right, be any embedding of E into a fixed algebraic closure F bar of F containing F, which fixes E, which fixes F. Then tau of E is contained in K. So why is this the case? So if alpha has minimal polynomial, so let's pick an alpha in E, and let's say the minimal polynomial of alpha is m alpha of x, which has coefficients in F. Then tau of alpha is also a root of this minimal polynomial and k contains all of the roots of this minimal polynomial by the other characterization of Galois fields, Galois extensions, which are separable extensions. Right? So that shows it. That shows that any embedding E into the algebraic closure of F, which fixes F, is actually going to be embedded an embedding into K. Okay. So we have this theorem from the previous chapter on extending isomorphisms between to the splitting fields. And since Galois extensions are just splitting fields, we have this extension of tau from E to sigma of E. Uh, this gets extended to an automorphism of the Galois group K. And furthermore, sigma fixes F because tau fixes F. So every embedding tau of E fixing F is the restriction. Wait, every embedding tau of E fixing F is the restriction to E of some automorphism sigma of K fixing F. In other words, every embedding of E is of the form sigma restricted to E for some sigma in G. So every embedding tau of E fixing F is the restriction of some automorphism sigma to E. Sigma is some automorphism of K fixing F. Okay, so far we haven't, I haven't said how this is relevant to proving 4, which is about normal subgroups, but this is, I think we have to do this before we can get to that. All right, so we have the statement. Every embedding tau of E fixing F is a restriction of some sigma, which is an automorphism K fixing F. All right, now what's next? So two automorphisms, sigma and sigma prime, restrict to the same embedding of E. So we have sigma restricted to E is equal to sigma prime restricted to E, if and only if sigma inverse sigma prime is the identity. So in other words, I can just write this as is the identity on E. And this is the case. If this happens, then sigma inverse sigma prime is in the subgroup H because it's an automorphism which fixes E, and that's what H is. So sigma inverse sigma prime, or rather, hold on, sigma prime is in the coset of H by sigma. So, all right. So the distinct embeddings of E are in bijection with the cosets sigma H. Let's write this down. Embeddings of E over F, the embeddings of E that fix F are in bijection with the cosets of H. And we know that this is the degree of F by the previous proof of 2. Okay, so let me try to make this a little bit more clear. If I think I was all right. So we have E is a fixed field of K, is fixed field of H, and sigma, when restricted to E, takes E to another subfield of K. Conversely, any embedding tau of E into the algebraic closure of F is actually a restriction of some automorphism of K. And then if you have two automorphisms of K, the restrictions are the same if and only if they belong to the same coset of H. So I hope this makes clear why the embeddings of E that fix F are in bijections with the cosets of H. Two such embeddings are the same if and only if uh, they are in the same coset of H. Right? And all embeddings are restrictions of elements of G. So yeah. By part 2 of the fundamental theorem of Galois theory, the index of H and G is the degree of E over F. All right, now we're a little bit closer to what we're trying to prove. And notice that the embeddings E over F contains the automorphism group E over F. Because any automorphism of E is an embedding of E. All right, now I think we're gonna use the hypothesis, which is that we have a normal subgroup. All right, so, okay, so we're gonna start, so let's remind ourselves what part 4 is saying. It's saying E is Galois over F if and only if H is a normal subgroup of G. All right, so let's try to prove this. So E is Galois over F if and only if H is a normal subgroup of G. Right, so let's start from this side. E is Galois over F. This is true if and only if the automorphism group E over F has the same order as the degree of the extension E over F. And then by the equality above, this is true. So we have one direction always being the case. The embeddings of E over F always contain the automorphisms of E over F. But we want that and we also know that the order of the group of embeddings, hold on, or the number of embeddings of E that fix F we have is equal to the degree of the extension E over F. Now we want that the automorphism group has the same order as the degree of the extension. So what we want is that the number of automorphisms is big enough to equal the number of embeddings. So what we want is that every automorphism, what we want is that every embedding is equal to an automorphism. Every embedding is an automorphism. So this is the case, E is Galois over F if and only if each embedding of E is actually an automorphism of E. All right, now we're closer to the point. So each embedding of E is actually an automorphism of E. What this means is that the embedding takes E to E. So sigma of E to E. Remember what we said, that each embedding of E is just a restriction of some automorphism of K restricted to E. So if so each embedding of E being an automorphism of E is the same as saying that for every automorphism of K, it sends E to itself. Right. Okay, we still haven't shown that H is normal in G, but we've reduced the statement that E is Galois over F to the statement that any automorphism of K takes E to itself. Right. Now let's try to show that this means H is normal in G. All right. Okay, so let's pick sigma in G. So what it's saying is if sigma is in G, then the subgroup of G fixing sigma of E is the group sigma H sigma inverse. So saying sigma of E is equal to the fixed field of sigma H sigma inverse. Right? Let's try to show this. So let's take any automorphism in this group and see what it does to this guy. So it would take, let's pick tau arbitrary H. It would, and see how it acts on this field. Um, so we would have sigma tau sigma inverse of sigma of E, and then what happens? So sigma and sigma inverse cancel, and you get sigma tau of E. Since E is the fixed field, or E is the fixed field of H, we get that sigma tau of E is just E, so you get sigma of E. And so this automorphism sends this field to this field. So that automorphism is actually in the fixed field. Or no, sigma of E is actually in the fixed field of this subgroup. I don't know why that keeps happening. So we know that so we prove that sigma of E is in the fixed field of sigma H sigma inverse, and now we're going to try to prove they're the same thing, that it is the fixed field. So it says the group fixing sigma of E has order equal to the degree of K over sigma of E. Okay, the group fixing sigma of E has order equal to the degree of K over E. So But this is the same degree as the degree of k over e. All right. So this is equal to the degree of k over e, since the fields are isomorphic. Hence is the same as the order of h. Right. Hence sigma h sigma inverse is precisely the group fixing sigma of e. Yeah, this has order sigma h sigma inverse because they're conjugates. So we've shown containment. Sigma of E is contained in the fixed field of this group, sigma H sigma inverse, and we've shown that the degree of K over the degree of K over sigma of E is equal to the degree of the group that we're taking the fixed field of. So this is equality. Okay, so we have this. Um, all right. Okay, now let's go back to the statement that sigma of E is equal to E for all sigma in the Galois group. Since the correspondence between subfields and subgroups is a bijection, we know that the fixed field of sigma of E and the fixed field of E are the same if sigma of E is equal to E. So this is true if and only if the fixed field of sigma E, which is this guy, so the fixed field of sigma H sigma inverse, uh, oh, my bad. So first of all, sigma of E is equal to, yeah, all right. Sigma of E is equal to the fixed field of sigma H sigma inverse. So first of all, I'm just rewriting what this is. So this is that. So I just literally rewrote the sets sigma of E and E. And now I'm going to use the correspondence between subfields and subgroups. So these subfields are the same if and only if the subgroups are the same. So G this is equal to that. And now finally, this is the condition that H is a normal subgroup. All right. So let's recap what happened. So okay. So first of all, we proved that any embedding of E takes is a restriction of some automorphism of K. And then we use that fact to get that E is Galois over F if and only if um, sigma of E equals E for every automorphism of K. So when you restrict any automorphism of K that sends E to itself. All right. Then we proved that the fixed field of sigma of E is, sigma of E is the fixed field of sigma H sigma inverse. And we proved this using the degree argument, counting the degree of and order of these subgroups. So now we're going to go back to this statement, which is a rephrasing of E is Galois over F as sigma of E equals E for every sigma in G. And now we have this is equivalent to saying that the fixed field of sigma H sigma inverse is the fixed field, is equal to the fixed field of H. And by the bijection between subfields and subgroups, we have that this group this conjugate group of H is equal to H. And finally, that means that H is normal in G. All right. Now, all right, so we know that E is Galois over F if and only if H is a normal subgroup of G. And the rest that we have to show for part 4 is that the Galois group of E over F is so in the case that H is normal in G, the Galois group of E over F is the factor group G over H. So we've already identified the embeddings of E over F as cosets of H in G. And when H is normal in G, these embeddings are automorphisms. So the group of cosets G over H is identified with the group of automorphisms of the Galois extension E over F. So we've already done this. The group of cosets is identified with the group of automorphisms. Okay. Okay, now part 5. All right. So I think this one's quick. So I'll just take like maybe 5 more minutes to finish this. So what is 5 again? 5 is saying that you have duality between the lattice of subfields of K containing F and the subgroups of G. So what are the 2 things that we need to show? We need to show that if you take the intersection of 2 subfields, they correspond to the group generated by the 2 subgroups. And if you take the composite of 2 subfields, they correspond to the intersection of the 2 groups. And that's all you need to show to prove that they're dual. Okay, so let's do one of the statements. Suppose H1 is the subgroup of G fixing the subfield E1. So I'll write it like this. E1 corresponds to H1 and E2 corresponds to H2. So we have 2 things. H1 is a subgroup of elements of G fixing the subfield E1. So this is the things in G such that sigma of E1 is equal to E1. And this is the automorphisms which fix E2. Okay. Now let's look at the intersection of H1 and H2. H1 intersect H2. And any element in the intersection of H1 and H2 fixes both E1 and E2. So any sigma in here fixes E1 and E2, right? Because you're in H1, which means you fix E1, and you're in H2, which means you fix E2, right? So any automorphism in the intersection of H1 and H2 fixes E1 and E2. So it fixes the composite E1, E2, right? Since the composite is just um, the algebraic combinations of elements in E1 and elements in E2. And if you fix everything in E1 and fix everything in E2, every algebraic combination is also fixed. Okay. So the fixed field, so E1, E2 is contained in the fixed field of H1 intersect H2. And we want to show that it is actually the fixed field of H1 intersect H2. So let um, um, let sigma be an automorphism that fixes E1 and the composite E1, E2. So sigma fixes I got it right. Sigma of E1, E2 is equal to E1, E2. So fixes E1, E2. So sigma fixes E1 and fixes E2. Why does it fix E1? Because E1 is contained in E2, E1, E2 in the composite, and E2 is contained in the composite. So if it fixes in this everything in this field, then it fixes everything in the subfield, and so on. So sigma fixes E1, that means sigma is in H1, and sigma fixes E2, that means sigma is in H2, and both of these statements together mean that sigma is in the intersection H1 intersect H2. Okay. So that means that the composite E1, E2 corresponds to the intersection H1 intersect H2. Okay. And similarly, the intersection E1 intersect E2 corresponds to the subgroup generated by H1 and